So next speaker up, Markus. He was also with us in Oslo in December last year. So he's very most welcome back to the conference. You didn't come to Las Vegas.
No, unfortunately I didn't.
You should have been there.
Yeah, I know. I mean, the weather's also better there, so.
No, it's not.
Okay, probably it's worse, but warmer.
Yeah. Well, again, another topic that I also think will be very interesting for the majority of the audience. And Markus, take it away.
I hope so. Thank you very much for the very kind introduction. Wonderful. So what I'm talking about today is what I'm calling useful password hashing. So it's about password hashing. I guess you all know what that means. And originally I applied for 30 minutes, then I had 1 hour, so I'm stuffing some more stuff at the end, stuff that I'm working about, and we'll probably do it in a voting way. So I'm proposing a topic, and you can say, hey, that sounds interesting, or that doesn't. But we'll come to that later. So first is about password hashing. Now, I'd say 95% of you knows what password hashing is. So last year, the kittens seem to have been kind of interesting. So here's a kitten for those that are bored by what's on the left side of the slide. For storing passwords, we all know that we shouldn't store them in plain. Still enough sites do it, but they shouldn't. You should also salt them. So you're choosing a random salt. You are computing some hash function h star, which can be a hash function, can be an iterated hash function, can be something else. It will be something else in the sequel. And then you're storing S and H on the hard disk. And to verify, you are just recomputing the value H given the value S that you're retrieving from the file. And then you test if the stored H is equal to the H that you recomputed. Now, of course, you all know what an offline guessing attack is. If the adversary learns S and H, then he can guess a password candidate, verify if that one is correct, and then we just start that process over and over until we finally find a password candidate PI that matches that verification here. Now there are two ways to improve the security of passwords against offline guessing attacks. First is by making the user choosing stronger passwords, which we usually fail to do. And the other point where we can improve the situation is by making the process of verification slower. This is basically what all the constructions are doing. We've seen an example of bcrypt yesterday. Bcrypt is pretty slow, and therefore it's considered relatively secure. Now, what I just said, the slower this H star is, the more secure it is against the offline guessing attacks. However, the slower it is, the more annoying it is for the server operator because he's spending more computational cycles on computing that hash function H star. Some numbers, you're probably well aware of those. Plain MD5 is pretty fast on graphics cards. Bcrypt is not that fast on graphics cards. And that's why bcrypt is considered more secure than MD5. Now, the thing is that even if that function is pretty slow, still, if we're looking at the RockU data set, we can do 100 guesses. If we are doing 100 guesses, we can still break about 5% of the accounts. Now just look at those numbers. Here, even the relatively slow bcrypt with 4,000 tests per second needs about 1/40th of a second for breaking 5% of the accounts. So this is bad, right? And if we say that an account should withstand, let's say, a minute of password cracking on that system here, which is not the best that you can do, of course. If you want to withstand for a couple of minutes, then you're ending up with several seconds for the hash function. And no server operator will ever be, that's my guess, but that seems to be true, will be willing to spend several seconds for just computing one password hash. So what could we do? And there's a disclaimer to come in 2 seconds. What we're trying to do is, if we are managing to make this computation of H star interesting for the server operator, if this is not just about burning cycles, but if this is about computing something that is interesting to the server operator, whatever interesting means for now. Good idea, doesn't work for reasons I'll explain in 5 slides or so. If we can use those cycles for something useful, then we hope that server operators might be willing to spend more time on password hashing. use stronger password hashes and therefore improve overall security. Now, that means that we are proposing to use H* to compute a solution to another problem besides of computing a password hash, solving some other problem, which we will call the base problem, and the resulting construction of H* will be called a useful password hash, UPH for short, and this is what I'm going to talk about the next 15 or 20 minutes or so. Before giving you more details and a better overview, disclaimer. This is academic research. This is not production ready for a couple of reasons. The program states something with the competition, which is technically not really true. We are not planning on submitting that to the competition because this is really research. This is nothing that we expect to be used in practice next year. And the other thing is, whenever you feel you have a question, just raise your fingers. Probably not now, but wait for the next slide. But starting then, whenever you feel you have a question, just feel free to interrupt me. And I might feel free to ignore your question, but yeah. Good. So again, the overall picture is you have a server. Let's say this server is doing the login, but at the same site, there is a large compute server which is computing something. Think of scientific computations, the big compute clusters. He's doing weather forecast, whatever. And we're somehow trying to combine that server with that computational power to get something which fits together and works well. Let's start with an example. I'm showing you a construction now where the underlying base problem is brute forcing DES. So brute forcing a DES key given a message and a ciphertext. Now you might argue that's not really useful, but that's just for the sake of the example because it's easier to present, and assume you're really interested in breaking a specific DES key, which is, by the way, kind of doable, 2 to the 56 operations. That's within reach. So the base problem is you are given a message and a ciphertext encrypted using DES with a key K0, and your goal is to find K0. What you're doing in practice is you're just trying out all keys K0, encrypting M0 under key 0, and you're getting a ciphertext. If you're hitting the right one, then you're done. That's how you usually solve it. Now, I'll show you how you solve it using a password hash. And what you're doing is you're picking a time big T. This is the time that your password hash should take to compute, which is, of course, an average time on a specific architecture, blah, blah, blah. And you're selecting a parameter gamma so that 2 to the gamma times T-des is about the time T that you want to have. So this means that gamma is selecting the bits of the key that you're brute forcing until, on average, you're finding a correct solution. Until, on average, you're spending time T. So gamma might be around 10 or something, 10 key bits. So probably it's a bit more, 20, whatever. Now, for storing a password, so this is about the function H*. For storing a password, you are selecting, first of all, a random value R and a random second part of the key suffix, which has size gamma plus 1. So this is the part that you're going to brute force later. And you're selecting a prefix, but not random, well, kind of randomly, but not choosing it uniformly at random, but by hashing this random value and the password together. So this is basically a random value based on the password, and we're salting it in a way by using that R here. This gives the second half of the key. So then key K1 is the prefix computed here and the suffix chosen here. So this is more or less a random DES key. Yeah, and it's a random DES key from a subset which is indicated by that prefix, which is computed from the password and R. Now what we're doing is we are using this key K1 to encrypt M0. M0 is from our challenge. This is part of the base problem we're thinking about. Encrypting that with K1, which is not the key from the base problem, probably not the key from the base problem, and we're getting a ciphertext C1. And in addition, we're using this key K1 as a salt in a normal password hash, let's say. This can be just any hash function, whatever. And what we're storing is, of course, user ID or something. We are storing the hashed value h, computed here. We are storing the random value chosen here, which gives us the prefix, if we know the password, and C1, which is from here. So yeah, C1 kind of serves as the identifier. This allows us to identify whenever we have the correct key, K1. And yeah, the K1 here is kind of used as a salt. I said that before. Okay, take a deep breath. Questions? We are basically choosing a random key and using that key as salt in another hash. And in addition, we're computing C1 as an identifier. We'll see in a second why we need that one. Okay, how do we verify a password given this string? How do we verify a password? Exactly, just plug it in the top and just recompute whatever you did. And that's possible, and that's the important thing to realize. You can recompute the prefix. Well, you can recompute something that is probably the prefix if your password is correct. This is K prefix here. We know the R. We haven't stored the suffix K suffix. So we have to iterate over all possible values. There are 2 to the gamma plus 1 values. On average, we will spend 2 to the gamma. So half of those here, 2 to the gamma. Remember, that's influencing the time big T from 2 slides before. We are putting prefix and suffix together to have a key K. And we encrypt M0 again with K, testing if this is C1. So if K is K1, the one that we had before, then this test will succeed. If the password is the wrong one, then we have the wrong prefix, and this test will always fail with high probability. For the wrong password, this test will always fail. If we have the correct password, then the prefix is the correct one. And then, iterating over all suffixes, eventually we will hit the right suffix. So eventually this K will be K1. So eventually we will have the right key. And if K here is K1, then this test will succeed, because this is exactly how we computed C1 on the previous slide. So this is why I said that C1 is the identifier. C1 allows us to identify when this key here is the K1 from the previous slide. Yes, and if we have the right key here, then we can use that key as the salt in the final hashing. And if the password is right, then this comparison will succeed. Otherwise, it will fail. Or we will even fail to find a suitable K over here. So now that's just not so useful, because that's just a password hash, but there's nothing useful to it. Now, what makes the thing useful is that we are computing a lot of encryptions here, and what we can do is a very short operation, we can additionally test if the outcome here, if that value here equals C0, which was part of the original problem. Remember, we wanted to find a key K so that M0 encrypts to C0. So if we eventually find a key K so that this test here succeeds, then we have solved our base problem. Then we have successfully brute forced the DS encryption that we started with. And I should say that once we did a password verification here and it was successful, then we should create a fresh password hash. So then we should start with that slide again, store the password in a new hash for being able to do new and useful computations for the next password verification. Okay, that was technical. I'm fully aware of that. And Per suggested putting kittens on those slides for distracting those that are not following. But do you have any questions about the construction given here? I will break it down to a slightly more informal level in 2 slides or so, or on the next slide. But do you feel like you can, or you want to ask questions here? Well, this either means that everybody understood or that nobody understood, which is a good start. But apart from the specific construction, let's take 2 steps back. What are properties that we want such a useful password hash to fulfill? Oh yeah, I have it here, right. So the general, I thought I moved it somewhere else. The general idea of the construction is you have a problem which is highly parallelizable. DES brute force is embarrassingly parallelizable. I mean, just test each key in parallel. You're selecting a subset. This was done by hashing the password and fixing a prefix. This should depend on the password because otherwise you can reuse the computation for all passwords you're testing. We are selecting a random instance from that subset by selecting a random suffix in the DES construction. We are solving one of those subproblems, computing a DES encryption. And then we didn't really split in the previous example, but we used the encryption directly as an identifier and then stored this tuple, the hash, an identifier, and the description of the random subset, which was the R in the previous example, because the R determined the prefix. So what are properties that the base problem or the entire construction should fulfill in order to be useful for anything? It should be interesting for the site owner, of course. The legitimate owner of the site should have an interest in solving that problem. Otherwise, he will not adopt the system. But it should be less or not interesting for an attacker. Now, the first thing here kind of hints at Bitcoin, how you correctly said. I mean, it would be cool if you could mine Bitcoins while doing hash verification. I mean, that sounds pretty plausible. Problem? This holds for the bad guy as well. So whoever is mining Bitcoins can just do password hashing for free. So bad incentives, unfortunately. And some technical problems because the hash chain is advancing and the latency, so the time between storing a password hash and verifying a password hash is pretty large. So you would need to frequently update that, and we don't know of any mechanism how to do that. Unfortunately, that would be really cool. Right, here it is. Better examples, potentially better examples. We don't, well, we know constructions for the second and third. We don't know one for the first one, but let's say it would be cool if we could do the exponentiations or the sum of the exponentiations in the SSL handshake using password hashes. The login server maybe is doing password hashing and SSL as well, or at least its servers close to each other. So if while computing password hashes, we could just use the modular exponentiation as a byproduct, that would be pretty cool. But that doesn't seem to work for a variety of reasons. What we can do is factoring, like factoring large integers. There are constructions where you can massage the factoring algorithm to a password hash. We can do DLOG computations. We even can do, and we have a pretty much working implementation for the Smith-Waterman local sequence DNA alignment, which is pretty cool. There the problem is you have a large part of DNA and you want to find small parts of DNA, not exact matches, but similar matches in that long part. And that's highly parallelizable as well, finding the correct position and computing similarity metrics for each position. That will work. And I showed you, and you have to believe me that it works. Example for brute force DES, which is purely academic, of course. Well, mostly academic, I guess. Anyway, more properties that we want to have is correctness, of course. Correct passwords should be accepted, otherwise it's pretty boring construction. Also, the solution to the base problem should be correct, because otherwise, well, there's no use of using the construction. Yeah, and all here we can assume that the server follows the protocol because he has an incentive for both correct verification and correctness of the base problem. Efficiency is another potential issue. It means that if the original algorithm for solving a base problem is much more efficient than when we were using a useful password hash to compute it, then everybody will use the original algorithm and the constructions are useful. So the time difference between solving the base problem on its own and solving the base problem using a password hash should not be too high. Yeah, that was the overhead actually. I apologize. What the first point here said is that the resulting construction H star should be about equally fast on the legitimate server and on the attacker's computer. Now we all know that those are never the same. Graphics cards, GPUs are much faster in solving, well, at least current constructions and probably all constructions that will come. So we can at most hope for being approximately as efficient. But that's good enough. All we are requiring is that there's no factor of 10 or so or 100 between the legitimate server and the adversary. Once you start using external data or even external code for relying on critical things like password hashing, you have the problem that the adversary might control the external input, either data or code to your algorithm, and the construction, of course, should tolerate that. It's not an issue at all for the DES brute force, unless, no, not even if he knows the solution, it does help him. So the DES example is resilient to maliciously chosen data, but there might be other base problems that are not resilient to maliciously chosen data. And you have to be careful in construction to consider that problem. And of course, we are relying here on non-standard cryptographic assumption, but we're doing that all day long, so that should be fine, I guess. But you have to keep it in mind that you're on shaky ground, even with standard password hashes, at least from a theory point of view. And of course, you want to be able to pretty much adjust the computational hardness. It should, of course, be pre-image resistant, but if it's not, then you're out on your own. Anyway, one important observation is that the H star does not need to be deterministic. So far, all password hashes are deterministic, so you can just recompute the value and compare. This doesn't need to be the case. It could also be probabilistic if you're choosing a more clever verifying function, which is normally not required. Here, it might be useful. Yeah, it can be parallelizable, which is a good thing, I'd say. I heard voices that disagree here. I hope you agree that password guessing should be parallelizable because it is anyway on the adversary side. So it's probably good if the honest server can also speed up computations by making use of parallelism. Yes, maybe it's a good point to ask for questions, because then I'm having some more general remarks on other constructions, and then we're doing a voting style continuation for the remaining whatever minutes we have. The thing is that similar constructions are not really only possible for password hashes, but also for proof of works. You probably all know proof of works from the context of spam prevention. They were proposed 100 million times to do so. I think they're not really deployed, are they? I don't think so, for a variety of reasons. But the thing is that you can also, using a similar construction, build useful proof of works, where you can outsource your computation to the prover in that setting, which is even nicer for several reasons. For example, latency is lower. In the password example, you have a high latency between storing a problem and doing the actual computation when verifying the hash. That can be days or weeks or months, and you are not even sure that one instance is ever going to be solved. For proof of works, the server is giving out the problem, and 10 seconds at most later, solution is coming back. So that's way easier to handle the parallelism. And you don't have to know the solution. You can match several solutions by different clients. And yeah, there are a lot of reasons why that is nicer. Red padding protocol is a related notion, which was proposed some years ago. And that's all I wanted to say about useful password hashes. And that was about half an hour. That was what I intended to do. That's great. So unless there are coming up questions now, yes?
Why did we don't simply do a wait loop of 2 seconds with no process or time?
The question is why we're not doing a simple wait loop for a couple of seconds before acknowledging that the password is right. This works for online guessing. So when you're logging into a vector server and the server is actually testing, then that's perfectly okay. And they're probably waiting longer. They're accepting 3 or 5 bad passwords, and then they start waiting increasingly longer, exponentially longer or something. This is done, right? Here we are concerned with offline password guessing. So we assume the attacker learns the stored password hash. And if he learns that, then any while loop, he can just discard. Yeah. Okay. So then I'm filling the question? No. I'm filling the remaining time for however long you like. Food is there, so choose wisely what else you want to know. Who wants to hear 3 minutes on implementing bcrypt and FPGAs? And I'm hoping you say yes, good, because that's a direct answer to yesterday's talk. Wonderful, thank you. It was very interesting to see that we are not the only ones trying to implement bcrypt on FPGA. We haven't done it, to be honest, but we're currently in the process of doing so. Interesting is at the University of Bochum, where I am, we have a couple of people working on hardware and security, let's say. And they built a machine called the Riviera, which is successor of the Copacabana, nice workplace. But anyway, which is basically an FPGA cluster. There's a picture of the older model of the Riviera, which had 128 FPGAs, features for programming them in parallel, a nice interconnect, which we don't really need. There's a PC, I think he's here, for controlling the entire thing. It has Ethernet at the end. And it's pretty cool because FPGAs are often very suitable for cryptographic purposes. That machine can brute force DES in 1.5 days on average. So it's pretty damn fast. And bcrypt seems like probably a good choice for implementing in FPGAs because they do not only have logic operations, they also have block RAM. We basically heard all that yesterday. So that's a nice picture of that machine. What you probably can see is here there are cards. You probably can see them better here. These are, I think, 16 cards with 4 FPGAs. So these are the FPGAs and some control logic. They're all sitting on a bus, and yeah, as I said, they can be programmed quite easily, also separately, but usually just the same. And yeah, here somewhere is the PC and the, I think here is the power supply. The interesting thing is, this is, depending on your problem, around, yeah, no, it's hard to say, 4 times as powerful as a GPU cluster that we tested, but that really depends on the application. The entire machine needs about 600 watts, so not much. I mean, that's just 3 graphics cards, and it's definitely faster. So yesterday's talk implemented bcrypt on something like that in the first line. Is that correct? Where are you? Here. Yeah, it's the right one. Yeah, good, wonderful. The old model of the Riviera uses FPGAs from the 3rd line, and the new model uses those from the 2nd line. And all the estimates that I'm presenting on the next slide, no, that slide actually, are using the 2nd line FPGAs. And we see they are kind of similar. They're slightly bigger in terms of logic units. The logic units are at least somewhat comparable. At least the numbers do match. That doesn't mean too much on FPGAs, but comparable, and the available block RAM is also about the same. We have estimates, we have no implementation. I have to say that again, we have no implementation, but we have estimates, and we believe that at least design A and probably also design B will work. And this will result in about 7,000 or 15,000 evaluations per second per chip. Times 64 chips, we are with 500,000 or 1 million crypts per second. Estimates. And it's slightly different hardware compared to yesterday, so the results are not really comparable, and we don't really know. And I'm telling you more next year, I guess. I hope. Good. Password strength and reuse. You probably know that already, but I can tell you we have a nice data set from malware, and we have numbers that, at least in the scientific literature, nobody has seen so far. Interested or not? Yay! At least 2. The others can leave the room. We do have a list of passwords extracted from a malware dump that a company, which is a subdivision of another company, yeah, whatever, collected over the years, or over the month actually. We extracted around 3,500 passwords. From those, around 177 were for financial accounts. So we were interested in comparing weak and strong, so unimportant and important passwords. We assume that passwords for financial accounts have a high value to the user, or at least that every user will understand that those are valuable. There's a difference between true value and perceived value, but we assume that financial accounts, they should have a high perceived value at least. So users should try to choose a strong password for those. And all the others are declared to be low value, which is of course not entirely true, but it's for the sake of comparing them with the certainly high value accounts here. Now what we did is we have 2 graphs, one on, yeah.
I would most certainly like to see a better variation in that you should also put in the privacy perspective, like your Facebook account. You have lots of details about your personal life in there. In your bank account, you only have money. So I would say 3 groups: the low value, the high privacy, and the high, financial value.
That's an interesting suggestion. The question or suggestion was to not only separate 2, but 3 classes, at least adding the accounts with a high privacy value, so to say. You mentioned Facebook. Why we didn't do it, because for Facebook, I think, and I'm pretty sure a large number of people will tell you, hey, that's only my Facebook account. I don't care about that account. So that's what I mentioned with perceived value, and this is not really, I mean, we don't know, but we assume that Facebook accounts have a pretty low perceived value on average, so not many normal users will try to choose a strong password there.
So perhaps we we should do a very simple study asking a select group of people to rank the personal value of a list of different types of websites or specific websites that they are using to see how is their perception of value.
I completely agree.
And then eventually we could compare to somebody else saying that this could be considered the real value of these.
Yeah, I agree. I agree to the statement that we should do a user study letting them rank the perceived value of accounts. Yeah, but we didn't. Definitely. Yes, so we wanted to compare those two sets of passwords. And the thing is 177 is not really that much for doing a statistical analysis. Also, we wanted to compare to other lists, Mt. Gox, for example, which is hashed only. So we used John the Ripper for comparing those, which is, of course, not the best choice from a theoretical point of view, but at least it's a highly practical comparison. So that's a nice graph. It has colors and all, but what does it say? And I have to say this is joint work with Stanberry. It says that, so the interesting lines are the black and the purple. Black are the low value passwords and purple are the financial or high value passwords. And we see that indeed, not that surprisingly, the financial passwords are, which is the lower curve, are indeed stronger than the financial ones. Even though we have, of course, a lot of important passwords in the bottom data set, so the really weak passwords will almost certainly be higher, but this is a combination of low and high, probably low and high value passwords. And these are only high value passwords. And there's a difference here. Yeah.
Not really a question, just a comment. There's a recent paper from Conrad Curley at Microsoft Research, and
which one?
some other people as well, where they have been looking at the use of graphical password strength meetups on websites to see if having a graphical password meetup will actually help improve people in creating strong passwords. And their simple conclusion was that yes, having a graphical password meetup will help people create stronger passwords. But if the account is of no value to them or perceived value, they don't care about the password meetup at all. I think those were the two findings they made in that paper.
Yep, that's interesting. I have to say we did not consider here why they're stronger, why they're choosing stronger or weaker passwords. We are just observing that they do. Of course, this might be caused by a better password strength meter on the financial side. This might be caused by a better password policy even on the financial sides. But the thing here is the important passwords, as they are now in the wild, are stronger than the weak ones. And that's an important thing to keep in mind when talking about passwords.
Yeah, I mean, in Norway, we are using two-factor authentication to log on to our online banks. And the password policy there pretty much sucks. You're allowed to use digits only and never have to change it. But they now have a minimum length of, I think it's 8 characters. And that's also one of the places where it's kind of fascinating to see them. That you can have crappy passwords, but still it's a perceived high value being a bank. But that's one of the questions I've been asking before is, will the introduction of two-factor authentication actually lower the quality of passwords because people will be using some kind of token or biometrics?
It probably will. And then the question is it a problem, or is the security added by the second factor outweighing the drop in security of the password?
It's not a problem until RSA gets hacked again and the root seeds are stolen.
Yep.
Because when that happened,
Definitely.
RSA said it's very important to have a good password. They didn't say that before.
Right. Also interesting, and that's probably known, is the comparison with MySpace, RockQ, and what else do we have? Carders, which are way less secure than those guys here, and Mt. Gox, which is more secure than even our strong set. It illustrates the important point that RockQ is a weak password set, basically. And it's weaker than what we experience in practice, according to our data set. Another interesting graph is on password reuse. We all know password reuse is bad. However, some forms of password reuse are worse than others. Reusing my password on my one German newspaper on the other German newspaper I'm reading is not a big deal, I'd say. Personally, some might disagree, but that's a kind of a tolerable form of reuse. A bad form of reuse is reusing my banking password on my online newspaper. And this has, to the best of my knowledge, not really been studied before. There are two kind of studies going that direction, but here we have nice data. Blue line is reuse in general, over all passwords, and green is reusing financial passwords on another site for the same user. Remember, we have data from malware. Malware captures several passwords per user, which puts us in a kind of unique situation here. On the x-axis, we have normalized edit distance, which means that 1 is completely different and 0 is completely equal. So if we are looking at equal, so exact reuse, we have those numbers here. Reuse overall in blue is about 14%, and reuse of financial passwords on another site is about 20%. Now I have no idea why that graph is above the other. I would have hoped, at least, for it being the other way around. I would have hoped, actually, for that point here being at 0. But it's not, for whatever reason. So people are reusing their financial passwords on other accounts, on low-value accounts. And this is bad, of course. Yeah.
Well, it's still quite small data sets, only the 177
Right.
financial accounts.
Right.
Yeah.
Yeah. Our data set is small. Here it's even slightly smaller because we did have the case that for one user we only had a high-value financial password. So the actual number here is even less. Yeah. But still, I mean, 20%, even if the error margin is 10%, we're still at least at 10%, which is bad enough. It should definitely be at 0. Good. Yeah. Is anybody aware of similar data sets? Probably there are lots of malware dumps out there. Does anybody know similar analysis of those data sets? At least in the academic literature, there's nothing. That's what I'm pretty sure about. Anything else? No, this is good and bad at the same time.
We have many password dumps, but it's rather rare that I see actually people doing comparisons between different data dumps from different sites.
Yep, there's one by Bono and somebody
else.
else.
Like 2-3 years ago with Sony and another site. He came up with a number of approximately 7% password reuse between two completely different sites and services.
I'm aware of that, but they weren't in plain there. He had to crack the passwords, and so he didn't have all passwords. And yeah, it was great. That's the one paper, or not paper, but the one analysis that I'm aware of.
As you also remember, at the conference in December last year, we the organization in Norway named Norsis, they actually made a survey in Norway where they asked 1,001 people about password habits and password reuse and stuff like that.
Yeah.
So I think there were some numbers in there as well on password reuse.
Yeah, there are plenty of numbers on password reuse from surveys, which is a good starting point, which usually have similar numbers than we have, but questionnaires on password usage are, well, not the best choice of analyzing them because people tend to lie occasionally.
It was something as simple as if you ask if are you really using the same password, they would think that you are more or less basing your question on the same word, but not if you have like first case, uppercase at one place.
Yeah.
People don't think like that. So if they are using password 1 and password 2, they will tell you that they are using the same password on 2 different sites, but they have a mixed case and they're using different digits at the end. But to them, it's the same.
And we nicely see that by using the edit distance here, so we see how fast similar reuse increases. Unfortunately, it's not that fast. But
I would really like to see more work on that one.
yeah, our data set is limited. That's why I'm looking for more on that data. Because it was really interesting, but limited by the relatively small number of financial passwords we had. Yeah.
Sorry. Can you say anything about how you managed access to the malware data?
Oh, yes. So Dan Bailey could tell you better. He would use, well, bad language for describing that. So, as I said, the data was collected by an Israeli subdivision of an American company, and of course they do collect malware data for helping their customers detect when passwords from their organization or from their users is leaked. Of course, they were heavily worried about that data being leaked somehow. That's why we didn't get the data, but only access to the data via several login and whatever hosts that try to prevent exfiltration of the data. Yeah, whatever. And it was a pain to work with because typically one of the machines crashed during the analysis, and then the entire chain was gone. And yeah, that's why he's using foul language to describe that. In the end, it was some database server and some Linux machine next to it that he could use the query. Then first he extracted all that looked like a password to the other machine, and we had a number of scripts there to run that gave us back data. I'm not fully aware of more details. Direct questions to him if you have more. Okay, one more topic to vote, fallback authentication. I was a bit worried proposing that, but now that so the web page says passwords only. But we have heard about tokens before, so I'm not worried too much. Interested?
Yes.
Good, great. Wonderful. What is fallback authentication? All of you know. You forget passwords, you lose security tokens, and you cut your fingers so that your fingerprint sensor doesn't recognize you anymore. This is bad, so you need a way to regain access to your account or to reset your passwords. There are many names for fallback authentication: account recovery, secondary authentication, password reset, whatever, you can name it. And of course, if the account recovery is less secure than the original mode of authentication, then the attacker will attack that. So that's, yeah, it has to be secure. You all know security questions, of course. They are, of course, not the best option. We all know that. You can do it by email or by SMS. Email can, of course, not be used for your email account as a fallback authentication, because if you lost access, then you lost access. SMS was not really designed to be a secure service, and we've seen attacks on those recently. But it's still used, and it's, well, probably not the worst option that you can use. By support team, it's pretty expensive, but often used as a last resort. By using another password, like the PUC for your mobile phones, and social authentication, that's what I'm talking about in a second. There was a question in the last row? No? Okay. Yeah. Sorry, can you speak up a bit?
I'm sorry. You've got there that there's a traditional solution for replacing biometrics and using a security token. I just wondered how email would help you with getting your biometrics.
Not to regain your biometrics, but to reset your biometrics, for example.
Reset them.
I guess. I haven't really thought about how you're resetting biometry, which is typically not easy, but yeah, unlock your account. Maybe selecting a password instead of biometry or whatever. Yeah, good point. I put that slide together in a hurry, or maybe I was distracted by the kitten. I don't know. Yeah, social authentication, harder than it looks, and that's what we experienced as well. we is in particular Ashar, who wanted to speak here, but then had some visa-related issues, and so he couldn't come here. So the next two slides were basically done by him. Social authentication is authentication by who you know, how it's often handled. For example, for Facebook, if you lost access to your account, then you can select 3 of your friends, 3 of your contacts. Random codes are sent to those, then you phone them asking for the code and entering the 3 codes to a web form or something. And if those are correct, then you can reset your password or so. I mean, there are 1 million variations of the same idea, but that's the basic idea. Now, there's an obvious attack. If you can make the victim to accept 3 of your contact requests, which typically everybody is accepting. He did a small test and had a pretty high turnout rate. 50% or so of his friends accepted fake requests. And then you can just, as an attacker, start the account recovery, selecting those friends that you control, and then the whole system blows up, which is bad. Countermeasures that you can use and that Facebook used in a previous version of the Trusted Friends, and apparently it's still used. You can only start the Trusted Friends account recovery if you have enough contacts, and probably also if enough contacts are old enough, if they're not only very new contacts and whatever. It's not really clear what they're doing. He talked to them and they revealed something, but not too much. And then Facebook is showing you in the first step a list of 100, so a sub-list of your friends of size 100. You can select 1 contact from that list. Then they're shortening the list to 50. You have to select 1 from the smaller set, and then they're shortening again. You have to select 1 from the last 25. This is apparently done to prevent the attack from the first line, where you are just choosing your contacts. And if you have enough contacts, let's say 300, then the probability that your controlled accounts are in those sublists, that should be pretty small, and then the system is at least more secure than it was before. Problem was that Facebook did not implement this correctly. They displayed the lists of the shrunken lists. But still, if you manipulated the headers and did some other tricks and jumped through some loops, then you could, in each of those steps, select the contacts from the entire list of friends. Which is, of course, bad because, well, they understood that they should show you a sublist, but if they still let you select your controlled accounts from the entire set of contacts, then you're, of course, in a bad situation, and that broke the authentication completely. The last time I spoke to Ashar, he told me that now they improved it by only letting you select it from the full 100 contacts from the first step, but in each of the 3 steps. So if you get your 3 contacts in that smaller sublist here, then you're still good. If you don't, then you're off. So it got better after we contacted them, but still not perfect. Questions? Yeah.
I talked a little bit to Ashar about this attack, and I'm really fascinated both about the concept and also the attacks that you have written about.
Yeah.
Do you know, first of all, do you know if there are any other sites that have something very similar to this one implemented today?
So you're asking if there are more sites that might be susceptible to a similar attack. The thing is, not so many sites are implementing social authentication because there are not so many sites having a friend list of yours. He was surveying a couple, I think 50 of social networks, and Facebook was the only one implementing really social authentication from those. If you are aware of more sites using social authentication in a similar way to here, I'd be interested to hear. Social authentication, anyone?
The simplest form I can think of is the typical example where you call help desk and tell them that you can't remember your password, and they will tell you that we will send you a new password to your manager, so go see him or her. And that's,
Right.
that's a kind of social authentication where
I'm
it
omitting
can also be attacked, of course.
I'm omitting a lot of details what he did here. That's just the basic idea. He also called a couple of help desks and got a couple of password resets that he should not have gotten. Interestingly, even he used an email address that was clearly from another guy, that had clearly a name. It was not the name that he claimed to be. And he wanted to have a password reset for another person. And he got it. Not even trying too hard, and it still worked. And I also omitted that he found a nice way to, so Facebook is sending out a couple of emails for making everybody aware of that an account recovery is going on, but you could drop the names of your contacts from most emails by manipulating the headers, and they didn't check on server side if those were formed correctly, and a couple of other nice things.
I've had a girl claiming to be a male calling help desk and saying that I forgot my password and she got it. By
Yeah,
phone.
great.
By phone, yeah.
I'm not surprised, unfortunately. Good. I think I'm now close to 1 hour. If you want, I can briefly tell you something about Android patterns. Again, it's not passwords, but it's still interesting. Yeah? Okay, I'm trying to do it quickly. There are quite many slides, and I'm trying to squeeze that a bit faster. I should have put a kitten here, but instead I put Sebastian Uhlenbeck, who actually did at least half of the work that I'm presenting in the next slides. PhD student in Bochum. I guess you all know the Android pattern scheme, the graphical password scheme from Android. You can skip it. Just let's say it's a restricted variant of the Passgo scheme. Passgo originally is bigger, had less restrictions. Android restricted it for usability and for some other reasons. I have no idea why they did it. For example, I have no idea why you cannot omit a point from a line, or why you cannot visit a point twice. The thing is, all these restrictions restrict you to, and I wrote the number, 389,112 possible patterns. And there would be many more if you didn't have those restrictions. But still, that high number is completely irrelevant because users don't choose uniform patterns from the entire set of possible patterns. But as you're all well aware of, they're choosing patterns from a much more restricted set. And the question we had was, how restricted is that set? So we all expected patterns to be weak, but the question is, how weak are they actually?
How many patterns were there, did you say?
Possible patterns, 389,112. There's no way to calculate that number. You just enumerate them using a small script, and then you're done. The selection process is so weird that there's no way to sensibly calculate that. So talking about the security of the patterns, you have to have patterns, of course. There's no list of patterns there, so we had to create one. So we did a user study asking for patterns. Now, if you're doing a user study on passwords or patterns, you have the option to ask a user for his actual password or pattern, which is a bad idea for a number of reasons. You can ask them to just create an account in your machine, just some throwaway account, and then whatever. This is also a bad idea because then they will choose a very weak, or there's the risk that they will choose a very weak password or a very strong one, just a random one. So you want to make them to recall the password after some time, after half an hour or so. Then they will choose a very weak one because they have to recall it. So what do? You have to balance the incentives for choosing weak and strong patterns or passwords, and that's what we did by going to our Mensa in Bochum and playing a game with them. When they entered Mensa, heading for lunch, we offered them some chocolate bars, but not directly, but they could create an account on an Android phone using the unlock pattern scheme. So they had to lock the account with a pattern. And then after lunch, they're coming back, they're reproducing the pattern, so unlocking the account, and then they get the chocolate bar. Good. So that gives an incentive for choosing weak patterns, because if they reproduce it correctly, then they get a chocolate bar. For this reason, we gave them an incentive to choose stronger patterns by telling them, and not only telling them, but we did it, that they are also attacking the accounts from the users before. So they chose their own pattern, Then they chose 5 patterns attacking the previously created accounts, and likewise the guys standing behind them in line, they attacked their pattern, and whoever broke a pattern from somebody else got their chocolate bar, and when they came back and nobody broke their account, then they got the chocolate bar. And you see that kind of balances, probably balances too much in the direction of strong patterns. We had a short pen and paper study on actual patterns, and the patterns that they chose here were a bit longer than the other patterns. So probably the data that we have is slightly stronger than the reality. Slightly stronger than the reality. But as we are set out to show that they're weak, it's good if we have stronger than reality patterns, and if those are weak, then the real ones are even weaker. Also, this gives us 2 sets of patterns. Defensive, these are the patterns that they chose to protect their account, and the offensive, those are the ones that they use to attack other accounts. And as expected, those are weaker than those, but we'll see in a second. That's a breakdown. We had 113 participants in that first part. As expected, the starting point is biased to the upper left. The transitions are mostly on the outer side of the rectangle. Only a few go in the middle. Those are the most frequent 15 3 grams, so 3 consecutive points, whatever. Then we used Markov models to model an attack based on the limited training data that we had. Tested a couple of parameters, whatever, and that's the first interesting slide. This is the actual attack against the patterns that we had. Good. How to read that? Of course, on the right-hand axis, this is the number of guessing attempts that we did. This is the guessing success, 1 here. Green are the defensive patterns, red are the offensive patterns. So the green ones are the interesting ones, and the true curve is probably slightly above the green, probably between the green and the red one. As I said, the green ones are slightly stronger than the true patterns. For reference, we have the guessing success for random 3- and 4-digit pins. So if you are choosing pins randomly uniformly, not user-chosen, and of course, for 3-digit pins with 1,000 guessing attempts, you have a success rate of 1, and with 5,000 for 4-digit pins, you have a success rate of 50%. And you can see that for a small number of guessing attempts, even the defensive patterns are weaker than randomly chosen 3-digit pins.
Yeah, but what is the point of this intersection? Because the intersection between 3.3 pins and green line.
The intersection is not interesting. Interesting is the following point. Let's say if you are doing, so on the Android devices, the number of attempts is limited.
Intersection.
The intersection.
The intersection to, right, yes, this one. What is the guess number exactly? Do you know?
No, I don't know, because
If it is more than 3, it doesn't matter whatever it's.
that's the point. This threshold is not really fixed. It depends on the Android version. One version that we had allowed 30 attempts. So what I'm saying is the crossing point here is not interesting. Interesting is for 30 attempts, what is your guessing success? Or for 100, depending on your Android version. I think for 30, it's 7 or 8%. Yeah, but showing the entire curve gives you a feeling on how it works.
So, in other
Yeah.
words, 3-digit randomly uniform, if you have 3-digit random is more secure than
Yes. That's how to read it. That's why I'm pointing to that region here. In that region, it's definitely less secure than a 3-digit pin, uniformly chosen, ideal 3-digit pin. Yeah.
But it's not really fair because both your offensive and defensive pattern, they're not random. They're chosen, but your pins are random. So did you try
This is not
random
about-
patterns?
This is not about fairness. This is no. Well, we're bashing them. That's obvious, but no. We are not comparing the security of pins and the security of patterns. Why we're showing that lines here is for reference, because 4-digit randomly chosen pins are typically used for locking a SIM card, often for your banking cards. Now the banks are allowing user-chosen pins as well, but that's a bad idea. It seems that 4-digit pins are accepted as a reasonable security measure against online guessing attacks. That's why we're showing that line here. And given the fact that this is way less secure than this line, we're showing that line as well for seeing where's the point. So we are not saying that patterns are better than pin numbers or something. We say user-chosen patterns are worse than uniform pin numbers. And that also is showing in the calculated entropy numbers. Here is the entropy for what you said, uniformly chosen patterns, but nobody will enter a uniformly chosen pattern, I can assure you. Uniformly chosen patterns are pretty good. There are 389,000 whatever. That's more secure than 6-digit pins, which should be fair enough. Yeah, entropy, this is how entropy is calculated, whatever. Now, given that here the results are kind of bad, we looked at, can we improve on the situation? Can we have small variations of the original scheme that are maybe more secure? And we came up with the following 4 variations. The top left point was the most frequent starting point, so we left it out. For forcing the users to start somewhere else. Unfortunately, everybody started at the top middle point. Then we're adding 2 more points because here's only 8 points. The original scheme is 9 points. Here it's 10 points. Let's see what happens. We have a random arrangement, also without a clear top left point. Also here, more patterns are possible because no straight line of length 3 is omitted, as it is here and here. And we have a circular arrangement just for the fun. Well, you never know. Yep.
What do you reckon would happen if you tried this in a country where there's writing from right to left?
Just the opposite. We didn't ask for nationality of our participants, unfortunately. Otherwise, we probably would have seen that in the data. But yeah, that's what we expect at least. Repeating the entire process again, 366 more participants that got chocolate bars. Most of them did, not all. And that's the result. The black curve is the defensive patterns from the previous slide. The red line here is the left out small, so without the top left point. There are less points, so it's less secure. We've seen that quite clearly. The left out large with a bit more points is the green curve. It's slightly more secure, but not that much. Interesting is the random arrangement, the orange line, which is, oh, I'm over time. The orange line is really insecure here. I'm not sure if you can see it. It's the least secure one, even though it looks pretty good, right? Why is that? You have any idea why the random pattern is really weak? Yep.
Follow the pattern.
It's a delta, right. Good, we didn't spot it when we designed the scheme. Quite a number of people saw a delta here, or an 8, or a delta starting here or something. So the thing is, the human brain is good in finding structure where there's no structure, and they found a delta. So random is a pretty bad idea. Yep.
Did you just choose that random one, or did you
just that one for all, for being comparable, because they're attacking other random patterns. We could not create a new one. Yeah. But in general, having random arrangements seems bad because, yeah, that's what's happening. Surprisingly, the best one was the circular arrangement, which was better than the original scheme of the entire line here, and it's better by more than a bit, so at least doubling the expected number of guesses, which is surprising because it has the same number of points. It's just basically moving the edge points towards the center, and that makes people create stronger patterns for whatever reason. We were a bit worried that a lot of people are choosing circles, but they didn't because probably they realized that drawing a circle is a bad idea. That's clearly insecure. So yeah, circles are pretty good. And that's it. Thank you. I apologize for being over time, but you had a choice. So, and enjoy lunch.
So, any more questions, Markus?
I have a comment. That's allowed.
Yeah. No.
I was wondering if maybe one reason the circular one is better is because you have more neighbors, so to speak. From anywhere where you start doing it, I think you can go to at least 5 other ones. But in the original model, you only have 3 neighbors in the worst case.
Yep, that probably was a factor. So the comment was that in the circular arrangement, you have more neighbors to choose from. And that's probably exactly what happens. On the other hand, the random arrangement, there are also more neighbors and more nodes are reachable. So in the random arrangement, every node is reachable. So that's of course, but no, that's not of course. Here, that point is not reachable from that point if this has not been selected before. Here, there's no straight line, so every point is reachable from every other point. That's how that was one thing that we imposed on the structure. Here, it's only that point that can be in the way. And I can tell you a lot of people chose like squares or that square, or they started a square and then got to the middle. So that, yeah, it was easier to select other points. Yeah. I'm a mathematician.
There are several principles in Gestalt psychology that might explain the results, especially between the random and the circle. And one of them is the principle of proximity. So the points that you have from the random, some are more close to each other than others, which creates even if it didn't create a letter or an alpha symbol, it still creates a logical path to follow.
Mm-hmm.
Whereas with the circle, they're all kind of equally close together, so there is no logical path to follow. So if you look at especially the principle of proximity, and even the other Gestalt principles too, because it explains most visual findings, in my opinion, as a psychologist. I would, if I were you, look at Gestalt psychology and then look at the proximity principle, because I think that really does explain especially your last two, the reasons why you got results for the last two
Okay, so you said that the principle of proximity explains at least those two and probably all the others. Yeah. I mean, that's wonderful. Thank you for that comment. We should talk more about that today or later. And it's fantastic. One question, then why don't too many people create a circle here? Because that's the most proximate one. Then I would have expected to have more circles.
You see it as a whole, not as individual parts, because they are so close together. I see it as like a little flower. Others might see it as like plants or something like that. I don't know, but I feel that because they're close together, that you see it more as a whole. So you're trying to create a pattern within the whole, as you're trying to create, rather than trying to create a pattern based on individual parts. Whereas with a square, a square is a square, but a circle can be seen as different things. If I were doing it, I'd create like a little star in it. That's what I would do.
So, Eunice and Markus are sitting together for lunch.
I'll send you a link.
Yeah, wonderful. That would be great. That's the computer science way of doing it. Great.
Okay, then thank you, Markus.
Thank you.